An active pixel sensor is an image sensor consisting of an integrated circuit containing an array of pixel sensors, each pixel containing a photodetector and an active amplifier. There are many types of active pixel sensors including the CMOS APS used most commonly in cell phone cameras, web cameras, most digital pocket cameras since circa 2010, and in most DSLRs. Such an image sensor is produced by a CMOS, and has emerged as an alternative to charge-coupled device image sensors. The term active pixel sensor is also used to refer to the individual pixel sensor itself, as opposed to the image sensor. In that case the image sensor is sometimes called an active pixel sensor imager, or active pixel image sensor. History: the term active pixel sensor was coined in 1985 by Tsutomu Nakamura, who worked on the charge modulation device active pixel sensor at Olympus, and more broadly defined by Eric Fossum in a 1993 paper. Image sensor elements within pixel amplifiers were described by Noble in 1968, by Chamberlain in 1969, and by Weimer et al. In 1969, at a time when passive pixel sensors that is, pixel sensors without their own amplifiers were being investigated as a solid-state alternative to vacuum tube imaging devices. The CMOS passive pixel sensor used just a simple switch in the pixel to read out the photodiode integrated charge. Pixels were arrayed in a two-dimensional structure, with an access-enable wire shared by pixels in the same row, and output wire shared by column. At the end of each column was an amplifier. Passive pixel sensors suffered from many limitations, such as high noise, slow readout, and lack of scalability. The addition of an amplifier to each pixel addressed these problems, and resulted in the creation of the active pixel sensor. Noble in 1968 and Chamberlain in 1969 created sensor arrays with active CMOS readout amplifiers per pixel, in essentially the modern 3-transistor configuration. The CCD was invented in 1970 at Bell Labs. Because the CMOS process was so variable and CMOS transistors had characteristics that changed over time, the CCD's charge domain operation was more manufacturable and quickly eclipsed CMOS passive and active pixel sensors. A low-resolution mostly digital N-channel CMOS FET imager with intrapixel amplification, for an optical mouse application, was demonstrated in 1981. Another type of active pixel sensor is the hybrid infrared focal plane array designed to operate at cryogenic temperatures in the infrared spectrum. The devices are two chips that are put together like a sandwich. One chip contains detector elements made in InGaAs or HGCDTE, and the other chip is typically made of silicon and is used to read out the photodetectors. The exact date of origin of these devices is classified, but by the mid-1980s they were in widespread use. By the late 1980s and early 1990s, the CMOS process was well established as a well-controlled stable process and was the baseline process for almost all logic and microprocessors. There was a resurgence in the use of passive pixel sensors for low-end imaging applications, and active pixel sensors for low-resolution high-function applications such as retina simulation and high-energy particle detector. However, CCDs continue to have much lower temporal noise and fixed pattern noise and were the dominant technology for consumer applications such as camcorders as well as for broadcast cameras, where they were displacing video camera tubes. Eric Fossum, al., invented the image sensor that used intrapixel charge transfer along with an in-pixel amplifier to achieve true correlated double sampling and low temporal noise operation, and on-chip circuits for fixed pattern noise reduction, and published the first extensive article predicting the emergence of APS imagers as the commercial successor of CCDs. Between 1993 and 1995, the Jet Propulsion Laboratory developed a number of prototype devices, which validated the key features of the technology. Though primitive, these devices demonstrated good image performance with high readout speed and low power consumption. In 1995, personnel from JPL founded Photodetector Corporation, who continued to develop and commercialize APS technology for a number of applications, such as webcams, high-speed and motion capture cameras, digital radiography, endoscopy cameras, DSLRs and camera phones. Many other small image sensor companies also sprang to life shortly thereafter due to the accessibility of the CMOS process, and all quickly adopted the active pixel sensor approach. Most recent, the CMOS sensor technology has spread to medium format photography, with Phase 1 being the first to launch a medium format digital back with a Sony-built CMOS sensor. Comparison to CCDs, APS pixels solve the speed and scalability issues of the passive pixel sensor. They generally consume less power than CCDs, have less image lag, and require less specialized manufacturing facilities. Unlike CCDs, APS sensors can combine the image sensor function and image processing functions within the same integrated circuit. APS sensors have found markets in many consumer applications, especially camera phones. They have also been used in other fields including digital radiography, military ultra-high-speed image acquisition, security cameras, and optical mice. Manufacturers include Aptina Imaging, Canon, Samsung, ST Microelectronics, Toshiba, OmniVision Technologies, Sony, and Foveon, among others. CMOS-type APS sensors are typically suited to applications in which packaging, power management, and on-chip processing are important. CMOS-type sensors are widely used, from high-end digital photography down to mobile phone cameras. Advantages of CMOS compared to CCD. The biggest advantage of a CMOS sensor is that it is typically less expensive than a CCD sensor. A CMOS camera also has weaker blooming effects if a light source has overloaded the sensitivity of the sensor, causing the sensor to bleed the light source onto other pixels. Disadvantages of CMOS compared to CCD. Since a CMOS video sensor typically captures a row at a time within approximately 1/60th or 1/50th of a second, it may result in a rolling shutter effect, where the image is skewed. For example, when tracking a car moving at high speed, the car will not be distorted but the background will appear to be tilted. A frame transverse CCD sensor does not have this problem, instead capturing the entire image at once into a frame store. The active circuitry also takes some area on the surface which is not light sensitive, reducing the quantum efficiency of the device. Thus, CCDs are preferred in astronomical applications. Architecture pixel. The standard CMOS APS pixel today consists of a photodetector, a floating diffusion, a transfer gate, reset gate, selection gate and source follower readout transistor, the so-called 4T cell. The pinned photodiode was originally used in interline transverse CCDs due to its low dark current and good blue response, and when coupled with the transfer gate, allows complete charge transfer from the pinned photodiode to the floating diffusion, eliminating lag. The use of intra-pixel charge transfer can offer lower noise by enabling the use of correlated double sampling. The noble 3T pixel is still sometimes used since the fabrication requirements are easier. The 3T pixel comprises the same elements as the 4T pixel except the transfer gate and the photodiode. The reset transistor, MRST, acts as a switch to reset the floating diffusion, which acts in this case as the photodiode. When the reset transistor is turned on, the photodiode is effectively connected to the power supply, VRST, clearing all integrated charge. Since the reset transistor is N-type, the pixel operates in soft reset. The readout transistor, MSF, acts as a buffer, an amplifier which allows the pixel voltage to be observed without removing the accumulated charge. Its power supply, VDD, is typically tied to the power supply of the reset transistor. The select transistor, MSEL, allows a single row of the pixel array to be read by the readout electronics. Other innovations of the pixels such as 5T and 6T pixels also exist. By adding extra transistors, functions such as global shutter, as opposed to the more common rolling shutter, are possible. In order to increase the pixel densities, shared row, 4 ways and 8 ways shared readout, and other architectures can be employed. A variant of the 3T active pixel is the Foveon X3 sensor invented by Dick Merrill. In this device, 3 photodiodes are stacked on top of each other using planar fabrication techniques, each photodiode having its own 3T circuit. Each successive layer acts as a filter for the layer below it, shifting the spectrum of absorbed light in successive layers. By deconvolving the response of each layered detector, red, green, and blue signals can be reconstructed. APS using TFTs . For applications such as large area digital X-ray imaging, thin film transistors can also be used in APS architecture. However, because of the larger size and lower transconductance gain of TFTs compared to CMOS transistors, it is necessary to have fewer on-pixel TFTs to maintain image resolution and quality at an acceptable level. A 2-transistor APS-PPS architecture has been shown to be promising for APS using amorphous silicon TFTs. In the 2-transistor APS architecture on the right, TAMP is used as a switched amplifier integrating functions of both MSF and MSEL in the 3-transistor APS. This results in reduced transistor counts per pixel, as well as increased pixel transconductance gain. Here, CPIX is the pixel storage capacitance, and it is also used to capacitively couple the addressing pulse of the read to the gate of TAMP for on-off switching. Such pixel readout circuits work best with low-capacitance photoconductor detectors such as amorphous selenium. Array a typical two-dimensional array of pixels is organized into rows and columns. Pixels in a given row share reset lines, so that a whole row is reset at a time. The row select lines of each pixel in a row are tied together as well. The outputs of each pixel in any given column are tied together. Since only one row is selected at a given time, no competition for the output line occurs. Further amplifier circuitry is typically on a column basis. Size the size of the pixel sensor is often given in height and width, but also in the optical format. Design variants, many different pixel designs have been proposed and fabricated. The standard pixel is the most common because it uses the fewest wires and the fewest, most tightly packed transistors possible for an active pixel. It is important that the active circuitry in a pixel take up as little space as possible to allow more room for the photodetector. High transistor count Hertz fill factor, that is, the percentage of the pixel area that is sensitive to light. Pixel size can be traded for desirable qualities such as noise reduction or reduced image lag. Noise is a measure of the accuracy with which the incident light can be measured. Lag occurs when traces of a previous frame remain in future frames, that is, the pixel is not fully reset. The voltage noise variance in a soft reset pixel is, but image lag and fixed pattern noise may be problematic. In RMS electrons, the noise is hard reset operating the pixel via hard reset results in a Johnson-Nyquist noise on the photodiode of OR, but prevents image lag, sometimes a desirable trade-off. One way to use hard reset is replace MRST with a p-type transistor and invert the polarity of the RST signal. The presence of the p-type device reduces fill factor, as extra space is required between P and N devices. It also removes the possibility of using the reset transistor as an overflow anti-blooming drain, which is a commonly exploited benefit of the N-type reset FET. Another way to achieve hard reset, with the N-type FET, is to lower the voltage of VRST relative to the on voltage of RST. This reduction may reduce headroom, or full well charge capacity, but does not affect fill factor, unless VDD is then routed on a separate wire with its original voltage. Combinations of hard and soft reset techniques such as flushed reset, pseudo-flash reset, and hard-to-soft reset combine soft and hard reset. The details of these methods differ, but the basic idea is the same. First, a hard reset is done, eliminating image lag. Next, a soft reset is done, causing a low noise reset without adding any lag. Pseudo-flash reset requires separating VRST from VDD, while the other two techniques add more complicated column circuitry. Specifically, pseudo-flash reset and hard-to-soft reset both add transistors between the pixel power supplies and the actual VDD. The result is lower headroom, without affecting fill factor. Active reset equals, a more radical pixel design is the active reset pixel. Active reset can result in much lower noise levels. The trade-off is a complicated reset scheme, as well as either a much larger pixel or extra column level circuitry. See also, angle-sensitive pixel, back-illuminated sensor, charge-coupled device, planar Fourier capture array, oversampled binary image sensor. References. Further reading, John L. Vampola. Chapter 5, Readout Electronics for Infrared Sensors. In David L. Shoemaker. The Infrared and Electro-Optical Systems Handbook, Volume 3, Electro-Optical Components. The International Society for Optical Engineering. ISBN 0-8194-1072-1. One of the first books on CMOS imager array design, Mary J. Hewitt. John L. Vampola. Stephen H. Black. Carolyn J. Nielsen. Eric R. Fossum, ed. Infrared Readout Electronics, A Historical Perspective. Proceedings of SPIE 2226, pages 108 to 119 doi, 10.1117/12.178474. CS1 Maintenance, Extra Text, Mark D. Nelson. Jerris F. Johnson. Terence S. Lomheim. General Noise Processes in Hybrid Infrared Focal Plane Arrays. Optical Engineering 30, 1682 1700. Bibcode, 1991 Opt N30.1682 and doi, 10.1117/12.55996. Stefano Meroli. Lenilo Cervelli. Daniel Parsieri. Use of a standard CMOS imager as position detector for charged particles. Nuclear Physics B, Proceedings Supplements 215, 228 to 231. Bibcode, 2011 New PHS 215-228 doi, 10.1016/J Nickel-Physps. 2011.04.016. Martin Vesey. CMOS Image Sensor Testing, An Integrated Approach. Jova Solutions. San Francisco, California. External links, CMOS Camera as a Sensor Tutorial showing how low-cost CMOS camera can replace sensors in robotics applications, CMOS APS vs CCD, CMOS Active Pixel Sensor vs CCD. Performance Comparison, A.